Hello everyone. I'll be teaching you today radioactivity, and we'll be seeing the various aspects related to it. And Radioactivity is class 12's second last chapter, and that is exactly nuclear physics. And radioactivity is a subtopic of it, and we'll be focusing upon the initial parts of radioactivity and and to start with, we will first have to understand what radioactivity is, why they is there. Why question I'll be answering later, but what exactly is radioactivity? We'll be answering it first. Okay. So whenever we say radioactivity, there's a one picture that comes in our mind, and that is this photo. Okay. Let me have my cursor here. So this photo we have in our mind of radioactivity. So is why exactly is this symbol chosen? So the answer is pretty simple. If you let me have my yellow pen. Okay, I guess I have selected it now. So if we have if we have a sun, for example, we know that sun emits light, and sun emits light in all direction. Okay, so this is light, and sun is emitting light. Okay, sorry for my background. Actually, I'm not using a stylus. That is the problem. But uh, please bear with me. Uh, this is our sun, and it is emitting light. Similarly, if you look here, if we consider it to be the nucleus, why isn't it looking like an? Let me use my mouse. Let me take 1 minute. Just yeah. So if we have a nucleus, then it's radiating radioactive energy outwards. It's radiating those alpha, beta, gamma particles. You might have seen the movie Hulk. What happens? Gamma particles enter his cell and then mutate and then cause that variety of havoc. So similarly here, even I will suggest you to watch the Chernobyl movie. It is, I mean, a really great movie about how radioactivity actually affected so many people, and most of it, even that was, I mean, very big tragedy. Mm, I mean, most of the people weren't even aware of that there is a radioactive surge in the town. They were just living with mm, they were just living in such a danger without even being aware of. So this is a nucleus, and it is radiating particles outwards. And the reason why is it three only? Why there isn't any four black these fan type symbols, and why not five six? There is a very long story behind that. I'll suggest you to watch how did we come up to these danger signs, biohazard signs, and then this nuclear hazard sign, and then you will get to know that. We'll be focusing upon the we'll be focusing upon, I mean, the major part, the important part only. If you're interested, then why not go and check out. So these are the heroes. These are these are not the only heroes, but these are the main heroes. These are one of those founders of this radioactive phenomena. Okay, so you will be knowing the name of Marie Curie, Madame Curie, and her husband Pierre Curie, and then there was this scientist called Henry Becquerel. Even the unit of radioactivity is named after him, Becquerel and Curie, two units of radioactivity. Okay, and just as here it is shown, we'll be discussing about alpha, beta, and gamma radiations. So that was just the intro part. Let's jump into him. Let's start. Okay, now, so we return here. So, uh, I was talking about radioactivity. So, I have already defined what is radioactivity. Radioactivity is the spontaneous decay of a nucleus. I can even show it to you how radioactivity actually occurs. Okay. Um, See here. This is the parent nucleus. For example, this is the parent nucleus and this is the daughter nuclei. We call the initial parent and the final daughter. Okay. No son here, daughter only. So this is the parent nuclei, and you see that four subatomic particles. In this case, the subatomic particles are protons and neutrons. So four subatomic particles have left this nucleus, and then there's a void created here. I mean, the whole of the this nucleus has decreased by four subatomic particles. That's what decay means, right? Decay means what? Decay means breaking out. So four particles have broke out from the parent nuclei, and then we get the daughter nuclei, which has a decreased mass number, and the mass number has decreased by 4. What is A here? Uh, what is A here? Let me change the thickness. Okay, so what is A here? A is mass number, and what is Z? Z is atomic number. I guess you will understand that by 80 I am meaning atomic only. Z and atomic. I guess you get it. This is the A is mass number and Z is atomic number. Okay, so let's go back to our slides and see here. Radioactivity, as I told you, is the spontaneous decay of a nucleus. Okay, so we have three types of radioactivity, and they are called alpha, beta, gamma. Alpha, beta, and gamma, and the beta is further subdivided into two categories: beta plus and beta minus, and we will see why there are two categories of beta decay. Okay, so let's first talk about alpha decay. So what is here in alpha decay? uh, you see there is a parent nuclear X which has this A as the as the mass number and Z as the atomic number, and then we get this Y and this alpha. I was just basically highlighting them. We don't need to worry about the highlighting portion. I'll erase it. Yes. Okay. So what I have this is X. This X has mass number A and atomic number Z, and this is Y. Y has mass number A minus 4, and here we have alpha which has mass number 4. And what is this alpha mean? What does this alpha mean? This alpha is helium nuclei. So this is nothing but He nucleus, helium nucleus. Okay, so this is helium nucleus, and how is this helium nucleus? You can say that, sir, I am a layman. I don't understand. Why are you saying that this alpha is the helium nucleus only? So okay, no problem. I can show you that also. So imagine we have A helium atom, it has two proton and two neutron in its nucleus, and then it has two electrons. This is an electron and this is an electron. Okay, so we haven't done anything new. We have just removed this and this. We have just removed these electrons, and now there is 2 plus positive charge here, uh, 2 plus positive charge here, and this, because of this 2 plus positive charge, we are just calling it that, because it does not have any electron it is just, I mean, it is without electron. We are calling it a nucleus. And which nucleus is it? It is helium nucleus. Okay. uh, One more question you must be having, sir: what is the difference between mass number A and atomic number Z? So mass number is, let me write it here. Mass number is, mass number is proton plus neutron. So basically, all the nucleons you have. Nucleons are what? Nucleons. Nucleons are what? Nucleons are the particles that are present in the nucleus. We have three subatomic particles: proton, neutron, and electron. Electron we are not talking about. We are talking about the nucleus only. Electron is not present in the nucleus. So we have this proton and neutron, and the combined number of neutron and proton is what we called it as mass number. And now, what is this Z? So Z is, some people call it Z, some call it Z. So let me call it Z. Okay. So what is this Z? Z is only the number of protons present, because mass number just don't tell us, sir, how many protons are there or how many neutrons are there. So we need to assign some number, so that we know that we have this much of proton and this number of neutron in the nucleus. So we will say, sir, then we know that there are some protons present. We know that there are some proton plus neutron present. How do we know that some neutrons are, how many neutrons are present? You haven't assigned any number here. How will we know that? So I mean, we don't need that. Okay, you can, if you just subtract Z from A, then you get neutron. Number of neutron is nothing but A minus Z. A minus Z. Okay, so you just subtract Z from A and you get a number of neutron. So there is no problem here. We have defined all the numbers from just two quantities A and Z. Okay, so this was kind of, if you are not able to understand what is A and what is Z, I have told you that. So we will be returning, I mean, we'll be focusing upon the decay part now. So what is exactly happening here? You can see that X is what? X is the parent nuclei. I will be using blue color, not blue color, red color to when I will be writing P with red color. Uh, this, just forget this portion. From now on, whenever I'll be using red color for P, it will mean parent nuclei, and red color for D, that will mean daughter nuclei. And when I'll be using yellow color, so yellow color would mean yellow color. Okay, so yellow color P and yellow color N, I'll be meaning that I'll talking about proton and neutron. So just for easy notation, easy difference, easy ability to differentiate. Okay, so this is the parent nuclei, and this is I'm really sorry, yaar, I'm really sorry. I did a mistake here. Uh, I'm sorry about that. This is the it was just an arrow mistake. This was the daughter nuclei. Okay, so what is happening here? X X is the parent nuclei, and alpha is breaking off from here. Okay, and then what we are getting left is a Y. Okay, So if I just try to show it to you, if I try to show it to you, then what is it? It is like X here, and alpha is breaking off, and then we get a Y. Okay, so this is known as alpha decay. This is a normal arrow. From X, alpha has broken off, and we have got Y. Okay, all right. So, hmm. So uh, I want you people to pay attention to one. To one very crucial aspect related to it. That is the mass number and atomic number in the whole of the equation. What do I mean by that? If you look closely, you will see that the net mass number in the left hand side is always equal to the net mass number to the right hand side. So here, if you will see that here it is it is that is not a good. I mean, hmm, yes. If you will see that here we have the mass number A in the left hand side, and in the right hand side we have the mass number A minus 4 plus this mass number 4. And when we will be adding the mass numbers in the right hand side, so A minus 4 plus 4, what is it? It is A. It is equal to the left hand mass number. And similarly, left hand atomic number Z, and if you will see the right hand atomic number, it is Z minus 2 and 2. If you add both of this, if you add both of them, if you add both of them, then you will get Z. Okay, okay. So 2 plus Z minus 2 is equal to Z, which is equal to the left hand atomic number. This is the universal relation, and I want you people to remember it. Okay, so now let's go on to beta minus decay. Why are we calling it beta minus? So if you look here, you will see that when after the reaction happens, we get a, I mean, after the parent nuclei breaks, we get a daughter nuclei plus an electron plus a antineutrino. Okay, so forget the antineutrino. Antineutrino is the fundamental particle. Fundamental particle is something which is not in our course, but I'll suggest you to look for the standard model. Okay, if you are interested, then you can search the standard model on internet, and then you will find we have different types of fundamental particles. Even proton and neutron are not that they aren't made of something else. They are even made of smaller particles, and they are the quarks. Okay, so we have multiple fundamental particles. So I will suggest you to search for the standard model on internet. For the time being, just know that there is a particle called the neutrino. Here it is the neutrino, and here it is the antineutrino. Okay, so we have seen that an electron is ejected whenever this reaction happens. Since we get a negative particle, we say that a negative decay has happened. So we call it beta minus decay. I hope you have got it. You will get a more clear idea when we will be reading plus beta plus decay. Okay. So what happens here. I want you to pay attention. It is X. Okay. It has mass number A and atomic number Z. When this nucleus decays in the beta minus form, then the mass number remains constant. There is no change in mass number, but a neutron here converts to proton. A neutron, if 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 this is a nucleus, I have this photo. Don't worry, I have this photo. Okay, so beta, it hasn't shown. I think it hasn't shown. It it hasn't shown beta plus decay. Oh, here it is positive. Okay, no problem. So you can see that we have a parent nuclei here and an electron plus an antineutrino eject out. And then what happens? Antineutrino is something which is just because of, which is emanating just because of the energy of the reaction. Nothing. I mean, it isn't. Uh, it it doesn't have any significance in the mass of the nucleus. So don't worry much about that. I'm again repeating because students do worry that why neutrinos and antineutrinos there. It is just to show that there is some energy changing here. Okay. So whenever an electron breaks out, so how does that electron break out? We are saying that, I mean, this is a nucleus now. So in the nucleus there is no electron. Electrons are around the nucleus. If this is a nucleus, then electrons are around there. This is an electron. This is circle. This is orbiting the nucleus. How come a nucleus here in the? How come an electron come in the nucleus? So an electron is coming from the nucleus because it isn't that the electron was already present there. No, here a neutron has converted to proton. So neutron has converted to proton, and to maintain the charge of the nucleus, to maintain the charge, we have we have I mean an electron exits out. Okay, just to maintain the charge, because if it was neutral, if it was neutron, it was neutral. Then a positive charge. I mean, let me show you here. It is a neutron. Suppose a proton P plus comes out of it. Then here the charge is zero. Here the charge is plus. How can that? How can this happen? How can a charge appear from, I mean, how can a charge appear from nowhere? It isn't possible. We have the law of conservation of charge, which says that, I mean, charge can never be destroyed nor be created. So how is it created from nowhere? It isn't created from nowhere because the charge is still zero, because we have an electron here. Okay, so whenever a neutron changes to proton, it exits out an electron. Okay, I guess you are getting some idea. Okay, so it is the beta minus decay, and note here that a isn't changing, that the mass number isn't changing, because there was a neutron, there's a and it has converted to proton only. So since neutron and proton have similar masses, so there is no net change. Okay, neutron to proton giving electron plus antineutron. And now we have this beta plus decay, which is just the opposite of what has happened here. The trick to remember it is that atomic number has increased by 1. Here what is happening? Atomic number has decreased by has decreased by 1. And why are we calling it beta plus decay? Because now a positive charge, I mean a positive charge exits out of this reaction. And the positive charge, we know that positive charge is carried by protons, but they aren't the only particles that carry a positive charge. There are particles that are called an anti-electron, or I mean more specifically a positron. So positron is what? It is just an anti-particle of the electron. For example, here we have this antineutrino. So we have this antineutrino, which is an antiparticle of neutrino. Similarly, we have this anti-electron, which is called the positron, which is the antiparticle of this electron. Okay, so a positron exits out. So why does it have? Why does that happen? This does happen because just I mean just this this happens just because of the opposite reaction. Here a neutron breaks out. Mhm. Well, wait 1 minute. Yeah, here a neutron breaks out into proton. Here a neutron converts into proton. I'm sorry, a neutron converts into proton, and here a proton converts into neutron. Okay, so this is the reaction. Here also mass isn't changing. The atomic number, the only the atomic number is changing. Okay, the mass is still the same, because electrons and neutrinos don't have any significant mass when we are talking about proton and neutron. Okay, and then this is the gamma decay. This is the simplest decay you will be, I mean, encountering. Why? Because whenever there is gamma decay, there is no change in mass number, there is no change in atomic number. I mean, I don't think you will be even having any question related to gamma decay, because I mean, the examiner cannot give you any question. Why? Because there is no change in that. He just wants to test that if we are able to calculate what change is there in mass number, what changes there in atomic number. So they can introduce gamma there, but there will be no problem, will be facing no problem because of gamma decay, because it is not having any role, it is not having any impact upon the mass of the nucleus as such. Okay, so then why, then if the mass number isn't changing, then what exactly is happening here? It is just that after some radioactive decay happens, the suppose, let me show it by energy. So suppose this is the energy. So this was the parent nuclei, this was the parent nuclei, and then it goes to a higher energy. The daughter goes to a high energy. Let me show it just like energy only. Okay, so it is the energy. Okay, so it goes to a high energy. So since it doesn't want to remain anything in the universe, wants to stay at the lowest energy possible, so it goes to the lowest energy, and when it loses out energy, it loses it in the form of gamma particles. Okay, so this is the gamma particle, and it exits out whenever the uh, whenever the higher energy atom, whenever the excited atom goes to a lower state. I mean, you say na that whenever there is in the atom also, whenever when the electron goes to a higher excited state, it just goes up higher in energy, and thus, and because of that, it goes to a uh, outer, more outer orbital, and then after that, it after it comes back, it loses out energy in the similar way. Okay, so for example, I have a question here, and I want you to people to pause this video and try this question. Okay, try this question, that if I have a nucleus X which has a mass number 230 and atomic number 90, and then one alpha decay happens, then 3 beta plus decay happens, then 2 gamma, then 3 alpha, then 4 beta plus, then 2 beta minus, then 3 gamma, then 2 alpha, then 3 beta plus, and then I have this daughter nuclei, the final daughter nuclei with this mass number A and atomic number Z. I want you to find Z and A. Please pause this video, and please pause this video and try to do this question. This is really really important. It is very simple, but it is really important for your understanding. Okay, so अरे प्लीज पॉज दिस यार, आई एम सेइंग ना. So okay, so how much time has elapsed? 28 minutes. Oh, so we have this Z and A. Okay, so how did we solve that? See, the initial atomic number was 90. Okay, so after beta plus happened, what happened is that we have this beta plus decay. So what happens here, you don't need to, I mean, do it at every step. I mean, just see alpha, then beta plus, then gamma, then alpha. No, this is not the correct way. The correct way is that count the total alphas you have here. So here you have 1 alpha plus 3 alpha plus 2 alpha. So 1 plus 3 4 plus 2 6, so we have 6 alpha. Okay, and then we have 3 beta plus 4 beta plus 3 beta plus, so total beta plus you have 10 beta plus, and then you have 2 beta minus. Okay, And there is gamma also, but you don't need to consider gamma because gamma isn't an gamma doesn't have any significance upon the atomic number or mass number. Okay, so yeah, so we have this 6 alpha. So if if we are talking about the atomic number, so tell me what types of reaction have effect upon the atomic number, all of the reactions. Okay, so it is 90 in beta plus. You are losing because you can see here that uh, proton has turned into neutron, so some positive charge is lost, so you are losing 10 positive charge, so you have it 90 minus 2, and then you have 6 alpha, so it is that 90 minus 10 positive charges minus 6 to the 12 positive charges, and then you have 2 beta minus. I guess there is some problem here in the question. Uh, uh, yeah, there is some problem. There's some discrepancy here. I guess uh, there's some problem here. So I'll solve it and I'll solve it separately. Okay, I'll solve it separately. Clear frame, clear frame, clear frame. I'll solve it separately. Okay. Hmm. I'll solve it separately here. So we had 10 beta minus 10 beta plus actually 2 beta minus and 6 alpha. Okay, so what happens because of we have this z, so what z is, that was 90, so 90 may say we will have to subtract 10, then we will have to add 2, then we will have to subtract 6 to the 12. So what is the final answer? The final answer is 90 minus 12, 78 plus 68, 78 plus 2, 80 minus 10, that is 70. So the question was correct, but I mean the way I solved it initially was, I mean, a bit shorter method. So just so that you people don't get confused, I solved it again. Okay, minus 10, whenever the beta minus happens, it adds positive charge, and whenever the alpha happens, it also subtracts, but in the factor of 2. Okay, and atomic number is very simple. You don't have to worry about that very too much, because I mean it is really simple. You see that it is really trivial. Clear ho ja. Okay, so atomic number. So atomic number, we have that what is the atomic number we have here? It is 230. Okay, it is 230. And now tell me, which of these three reactions, alpha, beta plus, and beta minus, have any impact upon the nucleus? Any impact? Only alpha has. Whenever an alpha decay happens, whenever a single alpha breaks out, a minus 4 decrement is seen in the in the final nuclei. So minus 4. Okay. So and whenever beta plus and beta minus happen, I've already told you that no change is there in the atomic number. So no change is there, atomic number there is change, sorry, I'm sorry about that. No change is there in the mass number. Okay. So it is 230 minus, we have 6 alpha, we had 6 alpha as you can see here, 6 alpha, and for every alpha there is 4, so it is 6 into 4, which is what, 230 minus 24, which is 204. I mean, you'll be saying, sir, these are just very very trivial things. Why are you explaining it really slow? Why are you explaining it like why are you explaining it? I mean, in such an such a depth. Why are you taking so much time? Our time is precious, sir. Yeah, I understand that. The reason I'm doing that because many people, I mean, most of the people I have come across personally, have this, I mean, severe aversion from this chapter, that I don't like radioactivity, I don't like nuclear physics, I'm not able to understand, even though they are able to solve, I mean, really tough problems of mechanics. So, because there is some aversion to this chapter, that's why I feel that we need to, and since it is very new concept, it I guess it only you first encounter it in your plus two only. So I feel that we I must be giving time to others to accustom to this new concept. Okay. So now we have this law of radioactivity, and what is this law of radioactivity? It is saying that if I have uh, an parent nuclei A and a daughter nuclei B, the number of subatomic particles that can decay there is n naught in A. Okay. This is the initial n naught. So it is saying that whenever A is decaying, the rate at which, you can see here, it is the rate. Okay. You can see here, this is the rate. So the rate at which it will decrease is directly proportional to what number of nuclei A had initially, what decayable, uh, what number of, I mean, what number of what number of, how much, yeah, how many decayable nuclei present were present in the sample. A is a sample. I'm sorry, I said it nuclei. A is the sample, and B is also a sample. B is the final sample, is the initial sample, and uh, the rate of radioactivity is always directly proportional to the number of nuclei, that can decay are present there. Let me show you, show you with, I mean, let me show you with some concrete example. Suppose there is a hospital. Okay. Suppose there is a hospital. Okay. And I'm not writing anything. So suppose there is a hospital, and every month all 10 people die the, from that particular hospital. Okay. So a government official comes and tries to check that if whatever I have said, whatever we have the initial data that 10 people have died, he just want to check that if there is any change, or is the old data equal to the, equal to the, if in present also this similar trend is continuing. So he just wants to check. So he comes, and he takes he considers two such hospitals which have 10 people dying every month, and when he surveys, he finds that 19 people have died. So he says that 20 people should have died and 19 have died. So some error, we can account to some error. There's no problem. So overall, okay, 20 is okay. They were right that we cannot account for 9.5 deaths. So they'll say that yeah, we are right that 10 people on an average die here. Okay, so what is the total number of deaths we have here? We have here 19 deaths. Okay, not 10 but 19 deaths. What if that person considers 100 such hospitals? What will happen then? Then obviously the number of deaths will be more. Okay, the deaths will be around 990 or 1000 or 100 1100. I mean, it will try if the trend still continues, then it will be more or less equal to the 10 multiplier case, that the number of hospitals into 10, so 10 deaths per hospital on an average. So here what you have seen, that the number of deaths is not just dependent upon that uh, a particular hospital only, or just not dependent upon how good medical facilities we have. The data of number of deaths we have also depends upon that how much we have looked into, how much hospitals we have looked into, how many hospitals we have taken account for. If I am just saying that there are 1,000 hospitals in my whole country, and then I just go and survey two hospitals, and then I find that 25 deaths has, 20 such that deaths have happened, and then I say that in the whole country 20 deaths have happened in this month. So I mean, that isn't that isn't a good survey, na? That isn't a valid result, because I have not accounted for all the hospitals that are present. Similarly here, the number of nuclei decaying will always depend upon the initial number of decayable nuclei. If 20 nuclei could decay, 20 will decay. Okay, I mean, if in a sample I had 20 decayable nuclei, then 20 will decay. And then after the decay, suppose that 10 have become non-decayable and 10 are still able to decay from that, then 10 will decay. I have a lower number of nuclei, then from 10 there will be 5, and we'll be able to understand all this after the concept of half-life. But I was just trying to give you an example, an idea that why rate of the rate of decay is directly proportional to the number of nuclei we already had. Okay, so this is the equation we have. Now we will derive it. We will say that, sir, at t equals 0, yeah, this is t equals 0, we have na equals n naught. At t equals 0, we have na equals n naught. Okay, all right. So we have that at t equals 0, we have the initial number of nuclei as n naught. So you will be asking me, sir, if I know this law of radioactivity, then can I predict at any given time t, any given time, after 1 second, after 10 seconds, after 1 year, after 1.5 year, after one you can say that 2 years, 1 month, 3 days, 4.55599 second. I mean, something very precise. Yes, the answer is yes. We can actually calculate that, and that is the reason we are studying here law of radioactivity. That is the reason that we can actually predict into the future that what is the exact activity we will be having. And this is the term that is this is called activity. The rate of decay. It is also called. I'll think I'll type it here. I'll type it here. Yes, this is called activity. Okay, and this is activity. uh, I think I should erase it first, because the arrow is looking a bit weird. This is activity. Okay, So minus dNA by dt is called activity. So now when we remove this proportionality sign, then we get this proportionality constant that is called the decay constant. I know this is a bit blur. I'll be rewriting this. Okay. Yeah, here. So let me clear this frame, and then I'll be deriving the law of the radioactivity equation here. Okay. So yeah. So we have this minus dNA by dt, and why minus here? Because whenever activity is happening, whenever there is radioactivity decay, then number of nuclei always reduces. Now that first we have 20, then we have 10 nuclei that can decay. So you will see that rate is also decreasing, because rate was dependent upon what? Rate was dependent upon the initial number of nuclei. Okay. So since the initial number of nuclei first was 20, and in the next decay it is 10 only, so initial nuclei is decreasing. So, so the rate is also decreasing. Since the rate is decreasing, we are having that minus sign. Okay. If you're not able to understand, just think about it. You will get it. And this is equal to lambda Na. Lambda is what? Lambda is the decay constant. I'm again repeating it. It is the decay constant. Okay. So now uh, we'll just reshuffle this. We will be having dna by na is equals to minus lambda t. Oh, sorry. uh, Minus lambda dt. Okay. So now since we have dna and dt, we can integrate it here. So we will integrate them, and 0 to t, and it was initially n naught n naught to, let's suppose we will call at nt, we will call it hmm, n naught, n of a at, just call it nt for now. Nt. Okay. It is nt. So we have the lower limit as 0 and n naught, and higher limits at upper limits at t and nt. So now what is happening, that we can say that integration of let me do it with a different color. Integration of dx by x is equal to ln x plus c, and c is the constant of integration. If you have done basic maths, then you will be knowing about it. Okay. So this is an indefinite, and definite we just focus upon the limit. There is no use of the integration. So now we have this, we have, you know here you can see that it was integration of dna by na, which is nothing but ln of na. And since lambda is a constant, it will get out, and it will be integration of dt, and this will become t. So what is this? This is ln of na, and not to nt is equal to minus lambda t, 0 to t. Okay, and so what is ln x? What is ln na here? Ln na is nothing but log to the base e of na. Okay, ln is log to the base e. So what it becomes? It becomes log to the base e na and not nt is equals to minus lambda t. Okay, so now what it becomes? It becomes if I just apply the rules here, it becomes ln. If I just apply the limits, it becomes ln n ln n t minus ln n naught equals lambda t minus lambda t. Okay, and because of this property, it becomes nt by n naught equals minus lambda t. So it becomes mt by n naught equals e to the power minus lambda t. Okay, and since it has become e to the power minus lambda t, so we have nt equal to n naught e to the power minus lambda t. So you have this equation here. I think I should use a different color. You have this equation here. This is very important question. This is the basic of the law of radioactivity, and this is the most important question. This is the most important equation we will be needing, uh, be it your boards, be it your competitive exam, be it your general knowledge, be it your interest. It is the most required equation. If you are studying nuclear physics, you ought to know this equation. Okay, so I will mark a star here also. So it's a star here, star. Okay, so that's it for today. I'll let me summarize what we have learned. Okay, it was just a basic lecture, and uh, in future we will be studying more complicated aspects of it. It was just an introductory lecture only. Yeah, so we studied about this this radioactivity model. How what do we mean by this symbol? Who were the founders of this stuff, of this very branch of physics? How radioactivity happens, what is mass number, what is atomic number, and how what is the relation in the left hand side and the right hand side, what is alpha decay, what is beta minus, what is beta plus, what is gamma decay, how do we calculate if we have a very complex set of radioactivity, complex series of radioactivity, and then this is the law of radioactivity, and then we went to derive what is this equation for radioactivity. Okay, so this was this equation for radioactivity. Okay, so uh, before ending this, I want to give you a homework question. It's a very simple question, but if you will try it, then I think it will be better for you to understand how the law of radioactivity actually works. Okay, so let me, you can take the screenshot of it. Okay, Yeah. So the question is that if after three lives it is here, okay, if after three half lives number of nucleus is 3 into 10 to the power 8. I don't have the initial number of nuclei this time. Just have I just have this information that after after three lives have happened, I have 3 into 10 to the power 8 nuclei, okay. Then find the number of nuclei after 5 t half. T half is what? T half is your half life. And since I haven't discussed the concept of half life yet, uh, uh, I ha- for the time being, I'll derive it also. But for the time being, just remember that after T half, I want you to do this on your own. So after I'm just giving you the information that after T half, what happens that n naught becomes n naught by half. Okay, so I have this concept of T half, but I will not be discussing it now. After T half, what uh, what does happen is that uh, let me search for it. What does happen that it becomes uh, n naught by 2. Okay, so here if I just try to write it, yeah. So after T half, after T half, T half. mm, uh, Let me use my stylus. Okay, so I'll erase this off. So what does happen after T half is that after T half n naught becomes n naught by 2. So it's just that number of decayable nuclei becomes half. Nothing rocket science is there. No sort of rocket science is here. So this is the basic concept, and I want you to solve this question about if you have this, if you have this 3 into 10 to the power 8 at after 3 lives, then what is the number of nuclei after 5 half lives? T half is half life. Okay, so that's it for today. Thank you so much for being with me, being so patient, and yeah, see you again soon. Thank you so much. Thank you.